metallicity, so about stars as fossil records of galaxy formation. So usually for dark matter in simulations, we have a relatively simple scenario of the hierarchical clustering of structure of dark matter halos, but the evolution of baryons is quite complex. So we have stars that build up metallicity, then they release all the chemicals to the interstellar medium again when they die, and then eventually this gas is recycled again into new generations of stars. And so slowly the galaxy built up the metal content over time. But this simple scenario is then complicated also with pristine gas inflows into the galaxy of low metallicity gas, or metal-rich outflows from galaxy centers, for example. So yeah, and stars are really the records where we can look at different stages of all these processes in the galaxies. So first of all, because stars can be very old, so we can go all the way back to the formation of the galaxy. And then secondly, the stars save a snapshot of the chemical composition of the galaxy when the stars were born. So thereby we can do galactic archaeology and reconstruct the star formation history and the chemical enrichment histories of galaxies. So by using this technique of galaxy archaeology, two important findings of galaxies are on the one hand side, the so-called galaxy downsizing scenario, where it has been found that massive galaxies assemble earlier and at shorter formation timescales. So usually when you look at the stellar populations in massive galaxies, you find very old populations which enriched very quickly. And then on the other hand side, we have the mass metallicity relation. So a relation between the total mass of a galaxy and its metallicity, which has been found for gas phase metallicity and stellar metallicity. So there are a few different explanations that come into play here, but most importantly, this is usually understood as that massive galaxies recycle gas more efficiently because they are more massive, they have higher potential worlds. And so they can retain the gas, and so it cannot outflow, and it can be efficiently recycled into new generations of stars. So where does this information about the stellar population come from? From the analysis of galaxy spectra. So we need to do spectroscopy, or we can do spectroscopy where we can get all this information. So we usually have the emission lines, of course, which probe the interstellar medium, the gas, which tells us about star formation, about gas kinematics, chemical abundances in the gas. And then we have the absorption lines, which probe the stars, the ages of stars, the metallicities of stars, stellar masses, stellar kinematics, and so on. Now, there have been huge advances in the field, where with using the technique of multi-object spectroscopy, we can take hundreds of galaxy spectra with a single shot observations. When we do this, there's a technical complication a little bit. If we were to just do this, just observe and then take the spectra, then we would have overlapping spectra on the CCD. So we need a way to rearrange the light path. So one way of doing this is to use optical fibers. As you can see there on the top right, so the optical fibers, they are plugged onto the observing plate, and then the light path can be rearranged onto the CCD, so they're not overlapping. And this technique can also be done now to do not only observe different objects, but actually observe one object, like one extended object, like a nearby galaxy, in a spatially resolved way. So we can actually, if we have the large extent of the galaxy, the field of view, we can cover the field of view with a lot of fibers, for example, and can get for different parts of the galaxy, in the center and the outer parts, and so on, spectra. So thereby we can combine photometry with spectroscopy. the advantages of having a spatially resolved way to look at the galaxies in 2 dimensions, and a 3rd dimension where we get the wavelengths, the spectroscopy. So it's called integral field spectroscopy. And this has really been a key, or is a key, to an increased understanding of galaxy evolution, because we can look at local scales and we can start to understand the internal processes in galaxies, what drives star formation, what drives the build of metals in galaxies, and so on and so on. So one of the integral field spectrographs is the BOSS MANGA spectrograph, which is shown here on the slide on the left-hand side. So where we have these fiber bundles and cover with each fiber bundle 1 galaxy, and we get spectra from the center of the galaxy or from the outer parts of the galaxy, and so on. Now, so there have been a number of integral field spectroscopy galaxy surveys in recent years, and people started to look at local relations, resolved relations, such as the mass metallicity relation that I showed you for galaxies as global relation. Now we can look at really different regions in galaxies on kiloparsec scales and see how the different parameters relate with each other. So for example, on the top here, so you have this star formation rate surface density and the stellar mass surface density, or the molecular mass surface density. And then you can plot these against each other. You see they all correlate somehow. So you have the resolved star formation main sequence on the left, and the resolved Kennicutt-Schmidt relation in the middle, and the resolved molecular gas main sequence on the right. And all 3 can be plotted together on the left-hand side, as you see in this 3D plot. So there's definitely some correlation between all 3 of them. And people have started to look at this in more detail. And then we can, apart from star formation and how this is driven, we can also look at the chemical evolution, so at the metallicities, and compare this with its stellar surface mass density, for example. So similar to the global mass metallicity relation, we can look at a resolved mass metallicity relation. So on the bottom panels on the left-hand side, we see the resolved relation between gas phase metallicity and stellar mass density. This was actually from the MANGA survey. And on the lower right, for the stellar metallicity and the stellar surface mass density. This was from the Khalifa survey for a sample of 300 galaxies. So for the stellar metallicity, the resolved relations, there haven't been so much work yet. And so this is where now my work comes in, that I present today. So we really wanted to make use of this large sample of the MANGA survey, which is about 10,000 galaxies, where we can look at resolved relations and correlations and try to understand what drives the stellar metallicity in galaxies. So we want to find out, like, how is the stellar metallicity locally connected to the stellar surface mass density, but also to the radius, the galactic centric distance, making use of the large samples, so we can look in different bins of global or total galaxy masses and morphologies. Okay, now I come to the MANGA survey. So I already mentioned it before, now in a little bit more detail. So the MANGA survey is a nearby galaxy survey that observes the integral field spectra, so the resolved spectra of 10,000 nearby galaxies. And that uses a BOSS MANGA spectrograph, which is mounted on the Apache Point Observatory in the US. And I already showed you on the lower left the picture. So it uses fiber bundles for each galaxy. And depending on the projected extent, the size of the galaxy, there are different fiber bundles of more or less fibers in order to have a uniform coverage of galaxies at different redshifts and different sizes of the galaxies. So in total, there are 17 fiber bundles. So we can observe 17 galaxies with one observation. And this was really the goal, to have this multiplexity, so we can go and observe up to, or we actually observed 10,000 galaxies. The spatial resolution that we achieve is about 2.5 arc seconds, which at the redshift of the MANGA galaxies is between 1 and 4 kiloparsecs. So we're really on the kiloparsec scales. And we have a large spectral coverage from 3,600 all the way up to 10,000 angstroms. And then these fiber bundles are all plugged on the observation plate, as can be seen on the lower right-hand side. To the sample, so 10,000 galaxies, a median redshift of 0.03, so nearby galaxies. The observations have been completed and the data release was just a couple of months ago. The sample was selected to be flat in stellar mass and in log, and to have a radial uniform coverage out to 1.5 effective Raday for 2/3 of the sample and 2.5 RE for 1/3 of the remaining sample. So on the left, I show you magnitude mass, a color mass diagram. And for the work that I did with the sample, I cross-matched the sample with the GR17 MANGA Deep Learning Morphological Catalogue from Elena Dominguez Sanchez et al. To have a classification into ellipticals, S0 galaxies, and late-type galaxies. So the main working sample that I will be using is a sample of over 7,000 galaxies. So the MANGA FIREFLY catalog, it's a catalog that we created of resolved stellar populations of the MANGA galaxies. And I will shortly present this to you. So what we do is to look at all the spectra across all the galaxies and to fit the spectra with stellar population models to obtain stellar population parameters such as ages or metallicities of these galaxies, which is shown here as a typical example. We have different model libraries. We use a master model library and the Miles model library. And a bit more detail about this. So the first stop, but I will be very quick at this point, not too many details. You can ask if you want to know more. First point, and so we need as first important ingredient the stellar population models. So we need to do stellar population synthesis to create a library of single stellar population models. The main ingredients there are an initial mass function, then some theories. So we need some isochrones or stellar tracks. And then we need a stellar library where this is based on. And as an example, one of the libraries that we use is the master MANGA stellar library, which is observed with the same instrument as the MANGA galaxies, which is very useful because you have all the same uncertainties, where you have the same wavelength coverage, the same resolution, and so on. And then you need to determine stellar parameters of these of the stellar library, such as metallicity, effective temperature, surface gravity, and so on. Much work has been done there by our PhD student at the ICG, Lewis Hill, but also by other groups across the MANGA collaboration. And actually for the master stellar population models, we use a combination of stellar parameters from the different groups that worked on this. So then we have the stellar population models. They're shown the spectra for some of those models. And each of these model templates have a known metallicity and an age. So it's in comparison are shown here on the left-hand side, just to illustrate the coverage of the different models of different ages and metallicity for the master models, and as compared to the Miles models as well, which we use as well in the catalog. And then as a second step, you need a code that fits these models to the spectra. So we use a FIREFLY code, which was developed at the ICG, a chi-square minimization fitting code. It fits the combinations of single burst stellar population models to spectroscopic data, and thereby it provides non-parametric, non-regularized star formation histories. So now we do this for every part of every galaxy. And then we can reconstruct. So we obtain the stellar population parameters and we can reconstruct two-dimensional maps across the galaxy of, for example, here shown for metallicity. So we provide resolved parameters of age, metallicity, mass, also remnant masses, star formation history, full star formation history, and dust attenuation. And then we also calculate global parameters such as radial gradients across the galaxy, central values, values at the effective radius, and so on. So in total, just to illustrate an overview, this is all the catalog is put together in one big FITS files where you have all the global parameters of the 10,000 galaxies, and then you have all the spatially resolved parameters, which are sets of stellar population parameters of over 3.7 million resolved regions. And this just shows you examples of two-dimensional maps of what I just said for 4 galaxies. From left to right, you have the stellar surface mass density, the age, metallicity, the reddening and remnant masses, and the signal to noise. Okay, so now we can take this and start doing science. Drivers of stellar metallicity in these galaxies. First of all, we can see, let's have a look if we can reproduce the well-known global mass metallicity relation. So now each point in this plot is a single galaxy, a galaxy as a whole. So this is the metallicity from the central 3 arcsecond of each of the galaxies, again plotted against the total mass in the galaxy. And we clearly see that we can reproduce the global mass metallicity relation. More massive galaxies are more metal rich. And then we can also separate these galaxies between late type and early type galaxies. And we see that early type galaxies have elevated metallicity as compared to late type galaxies. This is usually understood as a consequence of the quenching process, where the metallicity is elevated, increases much more quickly than the mass. But now we have all the resolved observations and all the resolved parameters. Now let's go one step further, one step deeper, look at the resolved relations. So this is a local counterpart to this relation. So this shows metallicity against stellar surface mass density. And first of all, here we throw everything in. So these are a plot that includes about 2.6 million resolved regions across all the galaxies. And we clearly see that there is a local relation. So we can see that surface mass density drives chemical enrichment on kiloparsec scales. Now we can, now we have the big sample size, so we can look at different galaxies as well, or different bins of the galaxies. That is shown here. So this is the same plot that we just saw, but now we separate the galaxies in different groups. So from left to right, we have galaxies of increasing mass. So left the lowest mass bin, and right the highest mass bin. And then from bottom to top, we have different morphologies: spiral galaxies, lenticulars, and elliptical galaxies. Well, first of all, we see that between the different morphologies, there are not many differences. So we see a little bit, if we look at the right-hand side, for example, we see that the gradient, the relation is a bit steeper in spiral galaxies as for elliptical galaxies. In general, in elliptical galaxies, the metallicity is higher, so it's more on the upper side here. What we just saw is just the consequence of the global relation. But there is a stronger dependence on the global mass. As we can see, if we go to the low mass galaxies and at the lower mass surface densities, this relation breaks down. So at the lowest masses, there's not much of a relation left. Now we have plotted the metallicity against the surface mass density. Now we can also look at the radial distance. So this shows metallicity against radius. And again, in the same grid of different types of galaxies. So different masses from left to right and different morphologies from bottom to top. In the background of each panel, you see the different, so these are the, from the parameters of the local parts of the different galaxies. So in each of the planets are hundreds of galaxies. So because we have this huge sample of galaxies here. In black, we show a running median, and then in orange, there's a linear fit to the inner part of this metallicity relation. So what we see here, again, there's not much of a difference for different morphologies. But we can see a strong mass dependence. So on the right-hand side, for the most massive galaxies, we have the steepest gradients. But when we go to lower mass galaxies from right to left, we see that the gradients flatten. And for the lowest mass galaxies, we have a quite flat gradient. And for spirals, it even turns around and is positive. So this, in general, negative metallicity gradients can be understood as a consequence of negative surface mass density gradients, which would drive these metallicity gradients. But apparently the metallicity gradients are not steep enough. So they're even flat or positive at the lowest masses, where also the metallicity surface mass density relation, as we saw before, breaks down. So there must be an additional driver of metallicity, probably a radial dependent driver of stellar metallicity in addition to the mass density. So why not plot against each other now all the three parameters: metallicity, stellar surface mass density, and radius? This is shown here. So for one part of the galaxy, so this is now just to show you one example. These are lenticular galaxies of intermediate masses. In this plot are 855 galaxies, local regions across these 800 galaxies. We plot the surface mass density against the radius, which has a negative gradient, of course, from the inner part of galaxies towards the outside. But we color code this importantly now with the average metallicity in each part. Now, first of all, when we look vertically here, so we will look at a fixed radius and we go from the bottom to the top. So we see that along the y-axis with increasing mass density, metallicity increases. So this is again the resolved mass metallicity relation. But we see that this holds true at each radius. So in the inner parts, in the outer parts, and so on. But then when we look horizontally, very interestingly now, when we look at a fixed surface mass density and we look along parallel to the radius, we see that at fixed surface mass density, the metallicity increases with radius. So we have just seen before that when we just plot metallicity against radius, we typically have this negative gradient, except for the lowest mass densities, lowest mass galaxies. But when we look at a fixed mass density, as we see here, then the metallicity increases with radius. So we need an additional radial dependent driver of metallicity, something that promotes the metallicity or the enrichment more strongly in the outer parts of galaxies. Or for example, we have a metal-rich inflow at larger radii, or we can have outflows in the center of metal-rich gas that can then rain down again at larger radii, like galactic fountains, or radial migration, for example. These are possible scenarios for this. When we look at the same plot again in this mass morphology grid of galaxies, so we did some statistical analysis, but just by eye, it can be rather quickly be seen that this trend can be found for most low to intermediate mass galaxies there. And then it kind of breaks down at the highest mass galaxies, and at the highest mass galaxies and low in the lower part here, lower surface mass density, it even turns a bit around. But interestingly, it holds true for the low to intermediate masses. This leads me to my summary. So yeah, we saw that with this big sample, we can reproduce the global mass metallicity relation. We found that early type galaxies have higher metallicity than late type galaxies at a fixed total galaxy mass. And then we could go one step further. Stellar metallicity is locally driven by surface mass density, at least for intermediate to high mass galaxies. So this is modulated a bit by total stellar mass and radius. And we saw also there's a strong mass dependence of metallicity gradients, which are usually negative, but become flat for the lowest mass galaxies. And if we plot these parameters together, we can clearly see that at a fixed mass density, metallicity is increasing with radius. So we need some additional driver, for example, galactic fountains, radial migration, or meteor-rich inflows, for example. And that would be all for now. Thank you very much for your attention. I take your questions.
Thank you very much, Justus, for this very nice presentation with a nice introduction, some very cool scientific results, and also for keeping the time as a schedule. So I have a few questions, but I will let the audience talk first if there is any question from other members of the ICE.
Yeah, I have a question.
Go ahead, Aldo.
Okay, so thanks, Justus, for the nice talk. So I have a couple very simple questions. One actually question and one some prediction for the future. So in particular to the last point, so how would radial migration help in this regard? Okay, I can see the metal-rich inflows and so on, but the radial migration is not so obvious to me. Why it would create this gradient, right? Inverse gradient, let's put it this way.
Yeah. Well, it's inverse when you look at a fixed mass density. But then when you can see, it can be seen if you have radial migration in simulations, for example, that they tend to flatten the metallicity gradient, which is usually negative. So if this gradient is flattened, just plotting metallicity against radius, then it can be inversed when you look at a fixed mass density.
Okay. And then the other question, the question is, okay, is there a chance of eventually disentangling alpha elements from iron in particular? So to have some picture of the alpha evolution.
Yes, definitely. So we did this not in this catalog that we produced yet, because these models also didn't have the alpha enrichment included, but we are for the master models, which are observed with the same telescope as well. We are currently working on this. So in an updated version of the models, there will also be different levels of alpha enrichment, and then we can try to study this as well in these galaxies. Okay. So this is definitely planned.
Okay, so you see well, I mean, alpha element features in the spectra you'll get and so on.
Yeah.
This is very okay. Yeah. Okay. Thank you.
Welcome.
I see Mar Mezcua has her hand raised.
Yes, hi, Justus. This is Mar Mezcua. Very nice talk. Thank you. I have a couple of questions. So first of all, do you see or have you studied whether there's any dependence on these relations on the presence of AGN and then on environment?
No, but this, so I haven't, but this is interesting and definitely something that can be done also because there's so many people working on the MANGA samples, so the sample of AGN, which are well characterized already, and also environment. There have been environmental studies already of the metallicity gradients, but not in relation to the surface mass density as well. But this is definitely easily possible in the future. Yes.
Thanks. Are there any other questions? You can also write them on the Zoom. In the meantime, I would like to ask you something. You see that the trend with radius and metallicity changes a little bit, in particular for the high mass galaxies. Do you think that is consistent with the satellite accretion of galaxies with lower metallicities?
Well, yeah, I think there's a possibility. Yeah, sounds. I haven't thought about this, but yes. I agree.
So in that case, as Mar suggested, it would be a very interesting project to study if these galaxies that have lower metallicities in the outskirts are located in more dense environments, so that would be more consistent.
Yes, that's interesting. Yes, thanks.
Great. And I have also, this is a little bit technical question, but I'm now studying a sample of galaxies which are interacting. So in the MANGA cube, you can see the 2 galaxies. Did you do any more curated analysis for these galaxies where you have contamination from different sources, or you just run the code as for the others, and we need to be careful with these sources?
Yeah, so the code to produce the stellar population catalog is just run for all the spectra that were from the data analysis pipeline classified as good fits from the so a good fitting flag for the data analysis pipeline. Then we just run our FIREFLY code on all these spectra. But for these scientific results here, I tried to include and I tried to exclude interacting galaxies or galaxies in pairs based on some catalogs from other people. Yeah, but I didn't, like for some residual galaxies, I didn't do an extra careful analysis or different analysis.
Yeah, I totally understand it. It's already too much work. I was just curious if you may have done a more particular analysis for those objects. Okay, thank you. Are there any other questions? Any final comment? No? Okay, so if not, please let's thank Justus again. Thanks a lot for the presentation. Keep in touch. Have a good weekend, everybody.
Thank you. Have a good weekend.
Thank you very much.
Thank you.
Bye.
Thank you.
Thank you. Bye-bye.
Thank you. Bye.
Bye.
Thank you. Bye.